Lesson 4 of Chapter 2 is on zeros of polynomial functions. We have discussed zeros of polynomial functions up to this point, and we have only focused on real zeros of polynomial functions. A zero of a polynomial function certainly is an x-intercept graphically, but we're going to start to venture into the world of some zeros will be non-real answers or imaginary values. Before we do that, let's talk about an equation. Here's a polynomial, second-degree polynomial, which means it's got two zeros. It's in standard form. Here's the same equation in a factored form. And when it's in a factored form, it makes it easy to identify the zeros. You can see that the zeros are -3 2/3. So having it in a factored form makes it easy to identify those zeros. If you look at the right, here's another polynomial of second degree in standard form. And you can see it written in factored form right here. So the zeros are plus or minus the square root of 5. So this leads us into how some of our zeros are going to be rational numbers, which simply means it can be expressed in the form of a fraction. And some of our zeros will be irrational, which means it cannot be written in the form of a fraction. And as a decimal, it would be a non-terminating, non-repeating decimal. Quick shout out to my main man, Brandon Harlow. He's out doing work in the trenches, delivering, passes and notes to people, just, giving of himself. He's a service guy. So shout out to the big man. So the next thing we're going to talk about is the rational root theorem. The rational root theorem is laid out right here. You learned it for the first time in Algebra 2. It talks about factors of your constant and also factors of your leading coefficient. And so I'm going to try to take this theorem and try to explain it to you in a more simple manner. So example 1 gives us a fourth degree polynomial, and it says list all possible rational zeros of each function. To do that, we have to use the rational root theorem. So what I need to do is come up with factors of p, which in this case is the constant -9, and factors of q, your leading coefficient, which in this case is 1. So the rational root theorem is any possible rational roots is p over q. So numbers that go into 9 are 1, 3, and 9. And numbers that go into 1 are just plus or minus 1. So your list of possible rational roots would be any of the p factors over any of the q factors. So in this case, we have 6 possible rational zeros. +1, +3, +9, -1, -3, -9. Well, then the next part of the problem says determine which, if any, of those are actually zeros. So then we graph the function, and I've got it graphed right here, and we take a look at the zeros. So as I look at the zeros here, I can see one right here, and that's at -3. So it looks like we have a rational zero at -3. The next one appears to be between -1 and -2. So that one appears to be an irrational zero, because if it was a rational zero, it'd be listed over here in our list. The next zero appears to be a rational zero, and that looks like it's at -1, and that's in our list. And then the last zero looks like it's between 1 and 2, so that must be an irrational zero. So we have a list of possible rational zeros. Then we identified any of them that are actually zeros. Let's do another example of the same kind of problem. Here this is a third degree polynomial, which means it's got 3 zeros. To come up with a list of possible rational zeros, I have to have factors of p divided by factors of q. So numbers that go into 2 are just 1 and 2. Numbers that go into 1 are just 1. So my list of possible rational roots are just +1, +2, -1, -2. Pretty easy to come up with this list when you just have 1 in the denominator. I'll show you in my next example where we'll have more than one value there. So now to determine if any of these are actually zeros, we graph it, take a look at the zeros. Looks like we have one right here that would be an irrational zero. Looks like we have one right here that would also be an irrational 0, and the last one right there is a rational 0 at positive 1. So to kind of bring this all together, same kind of problem here. I've got a third degree polynomial. If you look at factors of 8, those are the numbers written in blue, 1, 2, 4, and 8. If you look at factors of 3, those are the numbers written in red, 1 and 3. So our list of possible rational zeros are any of the blue numbers, excuse me, any of the blue numbers divided by any of the red numbers. So we get 1 over 1, 2 over 1, 4 over 1, 8 over 1, 1 over 3, 2 over 3, 4 over 3, 8 over 3. So that's your list of possible rational zeros. Then to determine if any of them are actually zeros, we have to graph it. So as we graph it, we can see 3 zeros. Looks like we have one at -2, and that's in our list. Looks like we have one between 0 and 1. And we've got some values between 0 and 1. I'm pretty sure that that's x equals 1/3. If we had a graphing calculator out, we could trace it to make sure that that is the correct 0. And then the last one right here also appears to be in our list, and that is x equals 4. So two things you have to do is come up with a list of possible rational zeros, and then find out if any of them are actual zeros. This is the rational root theorem. Last thing I want to go through is just solving an equation. So you can see here we've got a picture of a graph. If you're asked to solve the equation, I just need to know values that make it equal to 0. So in this case, it's -4. Now this 0 at -4 has multiplicity 2. And the reason we know that is because it doesn't cross at -4, it just touches. We'd also have a 0 at 0 of multiplicity 2, because it doesn't cross at 0, it just touches. And then we also have a 0 at 3. So that's how we'd solve the problem, is just to find the zeros. You can see the middle graph, we've got 4 x-intercepts. So to solve it, we would just say -2, 0, +2, +4. And then the very last one, disco guy Randy, we got 3 x-intercepts. So to solve it, we'd say it's x equals -3, because it crosses at -3, -1, and also at +1. Last problem here. If you're given an equation like number 44, and it's in standard form, not in a factored form, and it says to solve, what you need to do is you need to graph it. And then once you graph it, you can identify the zeros, and those are the solutions. So in this problem, we got +1, we got +2, and we got +3, and that is multiplicity 2. Because it doesn't cross at 3, it just touches. So we take a graphical approach to solving these problems.